Assalamu alaikum. I hope all of you will be quite fine. For the today's lab session, I will be giving the demonstration and instructions for this problem figure 2.110, and the statement for this problem is here. Problem number 2.112 through 2.114, and this figure is relevant to problem number 2.112. So as it states, derive the equation of motion, find the nature of frequency of vibration of the system shown in figure. So actually our main problem is to model the system and simply determine its frequency. So as we observe that here the linear damper is also available, and the spring of stiffness K is also given. We will be assuming some suitable values, and we will first be modeling the geometry for the system, and later on will be adding this spring and damper and its suitable values that I will be stating. So let us start. So let us start with the module. And first create the geometry in the design modeler system. And the system has been loaded. After that we will simply be using XY plane and put in the sketch view mode. Simply go into the sketching, and here as we can observe, actually our basic model is this sphere of radius r. So create this circle of some known radius. For example, you can take the radius to be unit, means 1 meter, and again move the dimensions a bit closer so that better view is available. So as you can observe that sphere, now our important task that will be we will be creating here. Actually it is the solid model, so we can create the solid model, but instead of creating the solid model, you can also create the surface model and give it some suitable thickness. So let us create a surface model. So go into the modeling, and here click on sketch and concept, and here surfaces from sketches, and click on apply and add material. It is all okay, and here you can observe, if you observe here, that its thickness must be greater than 0, so give some suitable thickness. So for example, you can say just 0.1. So that should not be 0, that must be some appreciable value or some suitable number. So simply generate and here you will be observing that a surface model has been generated, and regardless it has actually you can say it is actually showing the plane of the extruded model. So all surfaces will be parallel with this plane. So uh, and this surface model has been created sphere. Now our important thing that will be that its center is to be defined, because so that we are able to select its center. So center it will not be automatically be able to be located. So we will be creating you can say fictitious line body upon the center, though we can create a 3D point, but we will be obtaining the simple solution that we will be creating a simple line segment of negligible length and radius line body, and that will be actually connect as fixed with this center at this location. So in the same you can say xy plane for example, or you can say we will be creating that line body in the this yz plane, in this yz plane perpendicular to at the center. So click on yz plane and click on sketching and create a simple line body here. Just give it any suitable dimension. Here you can zoom in further and of negligible length. When vertical constant will be shown, then you will be clicking. So actually uh, sorry, this line segment can be anywhere on this axis, that we can create this line segment to be symmetric about this vertical axis. If we want, we can create this line segment symmetric, means half portion in this direction on the other side of the uh, surface model, and half on this side, or it can be anywhere, so that will not be making any difference. uh, its mass is negligibly zero, its mass is negligibly zero, and its length is very small, because this line segment is actually only created just to locate the center, so that the springs and damper can be attached with this point later on. So you can give it any suitable dimension if you want, or you can leave it as it is. For example, it says 0.003, so you can further reduce it. You can give any suitable value, and symmetry is not required, that is that will not affect. We will simply be uh, using this point, and we will be creating this line as a fixed with this surface body. So as it is very important that we will be creating this as the line body, we will not be leaving the sketch as it is. So line from sketches, and select this line and apply, and you can sorry, click this sketch, and you can simply generate. Instead of it must be add material, so that will not affect at all because this line is actually not separate. Now we will be assigning the cross section, so that is important thing. So we can assign the cross section. So we can assign the cross section to be, you can say 1/10 for example. You can say its length was 0.02, so you can say its radius to be 0.002 for example. So like this. Now we will be assigning the created cross section to this line, and we can here check out the cross section solids, and we can observe here that the line is negligibly and it is not actually visible. So in this way this model has been created. And now click on to model cell A4. So the model has been imported. So here in the geometry, what you will be doing, that you will be observing the properties for this created surface body. And the important thing is here that you will be going to its properties, and you will be observing its moment of inertia. So this moment of inertia that will be important, which is you can say about the polar axis, this moment. And furthermore, as you can observe for the line body, and if you observe its properties, it says its mass is this. So you can make it negligibly zero. So for example, you can create, for example, create an engineering material for this if you want, so that it does not affect our frequency. So here go into the engineering data. For example, just duplicate it here, and for example you can name it, for example, connection, or any suitable name, and give its density to be 1e minus 20 or any smaller value. And for this you can rename it to be, for example, sphere, a sphere, or you can say wheel. And give its if you want that its mass to be 1 kilogram, because we have used, so in the surface body, as you can observe here, its mass is this value. So we will be observing its volume is this. So what we will be, that is, if mass is unit means 1 kilogram, so mass per unit volume. So mass per unit volume, so we will simply be taking its reciprocal, 0.314 4 0.31416, and just take its reciprocal, so 3.183. So input, this has to be the density. You can just copy it from here, for example, up to 3 decimal places, and paste it here, and now you will be refreshing the materials. Refreshing the materials, and again you will be selecting the proper material uh, by doing it here. This is the sapphire, it is okay. So here you can observe that mesh has been transformed into unit, and here, so for this you will be selecting that connection. This will be the suitable material as a, so here you can observe the mesh is negligibly very small. So as they are that line body was actually a single body, so connection is not needed because that is actually fixed with that actually a single body. And otherwise you might uh, connect that line body with this surface body to be as the fixed joint. So if that requires, we will be later on be applying. So now the important thing is here, observe it in the planar view, and here the important thing now is that we will be connecting this damper and the spring, and because this is actually the ground, so you can observe it here that in the connections go into the insert and into spring, and here spring stiffness you can give it 1000 because I have assumed the value to be 1000. And after that we will be here selecting body dash ground, body dash ground, and here in the mobile we will be selecting if, sorry, the point, sorry, line. Here just wait a minute, let me observe it, what is the issue. Sorry, actually the problem that has been created, actually that was we will be actually creating in the geometry the line body to be as the add frozen. So this is important thing, so go back in the geometry, sorry, here in the geometry, and in the line body, sorry, here in the line you will be in editing selection, and here you will be transforming it to be add frozen, because that is actually the surface body and this must be a separate body. So now you will be generating it. So one is the surface body. Actually in the previous case when we had assigned the cross section, because this line body actually transformed at a single body with this circular shape, So that actually also converted into the line body, and it assigned the same cross section to this circular ring of the surface body as well. So that was actually the problem. So let us again observe the issue. If it persists, then we will be finding some other solution. So here you will be update geometry from source. So here you have observed that this is the surface body, and this is the line body. Let me again address it. Sorry, actually the line body, I think line body was wrongly selected. uh, Sorry, here edited selections, and actually this sketch was to be used. I actually sketch 1 was used, perhaps sketch 2 was to be used, so that was actually the mistake. So I assume again add frozen will not affect. We can leave it add material as before, so that will actually save adding the fixed point connection. So here, so this is the line body, so we will be assigning that cross section to this body. So now it has been corrected, and let us again go into here and update geometry from source. Here assignment, here in the assignment we will be assigning this material, and here we can observe it again that the mass is negligible small and the surface body, and it is actually unit kilogram, 1 kilogram. So now go into this connection here, and now that will be successfully applied. So here in the mobile we will be selecting the point filter, and again we will be zooming it. We will be you can say box zoom it like this, box zoom it, and sorry, here you will be now click on single select, and at this point, because this point was actually in the spherical surface. Here again, if you of the meshed body, so now click on apply, and after that we will be defining the reference coordinate. So you can observe it here if you put it in zoom to fit. So the spring length, because the radius for this is actually has been used as to be 1 meter, so we can use, for example, this radius is 1 meter, so we can assume the total length of the spring to be, for example, 3 meter. So this was actually, this point was at the origin, so this is at suppose along negative x-axis, so negative x-axis negative 3 units we can input. So in the negative direction we can input negative 3. So here, as you can observe, that spring has been placed, and after that we will be inserting another spring. And now the important thing that we will be inputting its longitudinal damping here to be as I have calculated the actual damping. Here you will be inputting the actual damping value, the that has been 25. So after that we will be observing, again make it body dash ground like this. And now in the reference, sorry, in the mobile, select the same point. Again you can box zoom it, and again here in the select mode single select, and at this point select it. And now because you can observe that here in the zoom fit, because this was actually the origin point, so the damper here you can say this point, same the damper length is also 3 meter, so we can input positive 3 along x-axis, positive x-axis. So input plus 3, so like this. And as we have observed that the spring damper has been applied. The one important thing that you have noted, that here in the longitudinal spring, the on the left side the damping was 0 because here was no damper. So it is an important learning in this lab session, because here the damping was 0 for this spring. The damper was actually placed at this side, so we have placed a separate spring connection, but the damping stiffness value for that spring has been 0, because you can observe it here. Longitudinal stiffness has been 0, but only damping actual damping value has been, not the critical damping constant here. So in this way, so after that in the analysis setting, it is very important you will be inputting the mode to be unit. And after that in the analysis setting, that is also very important here. You observe that in the rotodynamic controls, sorry, in the output controls, here you will be here in the solver control, sorry, damped, in the damped area you will be in selecting yes. By default it will be no, so you will be selecting it yes. And after that no other important setting is required. Perhaps in the damping control you can you will leave it as it is, you will leave it as it is. So here you can insert the deformation, but still important, sorry, important constant are to be still applied here. So one important constant here, as you can observe in the model, that the center of this sphere is actually translating in this direction, and this sphere is actually in pure rolling. So that means is a, sorry, a center positive in this direction, actually the center is actually displaced, and it will be rotating or revolving in this direction, so that the center moves in this direction. So we will be inputting here insert first of all a remote displacement, and we will be selecting this surface, and for this surface we will be because this surface is actually in pure rolling, so that means this is actually rotating, and at the same time it is actually you can say translating in the x direction. So here you will have to work and think, because this is very important. Think, if you get error you will again be trying. So let us first observe that input the linear coordinate to be free, y must be 0, and z must be 0, because in the perpendicular direction it is not moving. And in the rotation x must be 0, rotation y, because those axes are in the plane of the this body, this wheel, so that are also 0. But in the rotation z, because that is the polar or perpendicular axis, so that must be free. And in the behavior you can set it to be as a rigid. So another constant that can be applied at the center, which is actually you can say simply the displacement coordinate, because the center must be confined here. uh, Again, for example, in the z direction, here this point, again you can box zoom it, not this point, that point. Actually, again you can select it in the selection of single select here, this point has to be free in the x direction, and y must be 0 and z must be 0. Again we will still be deciding that this x should be free or not, so we will be deciding it from the results. And so let us solve it. So total deformation, so let us solve it and wait what happens. If any issue, we will be again trying. Solution has been successfully done, but unfortunately, as you have observed, that the damped frequency, it is actually showing 0. So let us resolve it. This issue. So don't worry if you are making any random analysis and you get some errors or any problem. So always be patient and try to resolve it. As so the problem was actually resolved, and the video was kept paused for a lot of time. Recording was paused, so the problem was actually investigated, and the issues that have been found and the solution that have been applied, they are one was that actually the fixed joint between the line segment, means here you can observe, if we box zoom it, so you will be changing these settings. So using this edge filter, you will be selecting this line body in the body dash body, and type will be fixed joint. And in the reference you can, for example, select the using edge filter as to be line body as the edge, and in the mobile you can select the face, or alternatively that will not affect. So this joint was actually mainly applied, and the other important thing that was actually applied, that was the planar joint. The planar joint means here you can observe, for example, this is the model. So planar joint was actually applied such that this sphere actually is in planar, you can say planar motion, for example, that it will be actually rotating, and its center will be translating, its center will be translating in the x direction. So actually only the planar joint worked. I have tried a lot and consumed much time upon investigation. So you will be applying a planar joint. No other joint actually worked and brought the nearest results. So in the planar joint, what could you do? That you can check it here, that body dash ground, the setting was body dash ground, like this, that this sphere is actually in the planar motion with respect to the ground, because this is actually the ground surface. So uh, here one setting is the body dash ground, and other setting is that in the mobile you will be simply be selecting here the face filter, and you will be simply be selecting this face, and you will be clicking on apply, and that joint will be applied, planar joint will be applied, and no other setting is required. So this planar joint and other longitudinal and damper and spring have been applied as before. They were not changed at all as in the previous recording before pause. And other important settings, analysis setting in the mode was 1, and here in the damped, in the solver control, the damped must be set to be yes if you want to calculate the damped frequency. And in the model, the important is the remote displacement. So two remote displacement were carefully applied. So uh, you will be applying two remote displacements. So remote displacement are such that one remote displacement applied to this spherical this circular face, this circular wheel face. So that was up. And now observe the setting, that the settings are free in the x direction, because this sphere is this circle, this circular wheel actually, it is free to rotate in the x direction, because its center is actually free to rotate in the x direction. So as I was telling actually, that in the remote displacement, in the remote displacement this spherical face was selected. And here it is very important thing that I have tried, that this face is moving in the x direction along x axis as well, and it is actually simultaneously rotating about z axis, perpendicular axis, means its center is actually moving in the x direction. So all particles will be moving in the x direction, uh, and it is actually rotating about z axis. So here if you at least you will have to put x component must be free. Z component is optional, it is not actually affecting the results. Practically you can make it to be constant, so the results were not actually changed. So logically if you can observe that because here in this direction, uh, practically actually you, if you are inputting that y must be free, for example, if y is free, so that actually means that this circle is actually moving in the vertical direction, but actually that is not the case. Practically its particles or constituent particles are actually rotating. So uh, that means they are changing in the y direction and x direction in their own plane, but actually it is as a rigid unit is not moving in the y direction. practically it is not moving in the y direction, its particles are moving in the x direction and y direction as a rotation. So you can observe that logically it must be pure rotation. Logically it must be pure rotation and center must be translating, but actually that is not giving the close results. So what I have tried and investigated, that in the displacement in the circular face, that must be x component free, and rotation about z must be free, and the other remote displacement is the line segment which was actually created in the center, that must be in free in the x direction, because the center is necessarily confined to move along the x direction, not in the y direction or in a, and it has zero rotation. So and behavior of both the face means the wheel and the line body must be rigid. So that were actually the important setting that were applied, and in the analysis setting, as I have already told, that in the solver control, damped must be yes, and no further setting is required. And when you will be solving it, when you will be solving it, you will be observing that this is the damped frequency that is actually resulting, and here this is the modal damping ratio. Now I will be orally speaking the values, and will showing you its theoretical solution from the solution manual. And here you can observe that actually this was the problem 2/112, and here the author has actually derived its solution, and regardless the methodology of the solution, the end result is this equation: 3 by 2m plus c x dot plus kx. And as you can observe that here you can say that means the equivalent mass is 3 by 2m, means the mass of the wheel, the mass of the disc or the wheel multiplied by 3 by 2, means 3 by 2 of the inertial mass of the wheel. So that is actually the you can say natural frequency, which is actually square root k by m. So k by m, so that comes out to be 2k by 3, 2k by 3. And when I have used the results, so the value which I got, that was in radian 25.82, means k was 1000 and mass for the disc was taken as to be 1 kilogram, and k was 1000 newton per meter. So this gave 25.82, and the frequency in hertz that I obtained, that was 4.11, that was 4.11, that was actually the natural frequency. And when its critical damping constant, as you observe that it is actually equal to 2m omega n, 2m omega n, and m was equivalent 3 by 2m. So it actually gave the result as to be square root 6 km, square root 6 km. You will be solving it yourself as you will be listening, and when we will be solving it, so critical damping constant that comes out to be, critical damping constant that comes out to be, remember this is the linear critical damping constant, mean this is the linear damper. So 77.4596, 77.4596. So that is actually the critical damping constant. And the actual damping means critical the given damping constant that has been assumed to be, because the system has been assumed to be under damped, so the value for C has been suggested as to be 25 Newton s per meter, Newton second per meter. So the damping factor comes out to be 0.323, 0.323. 0.323, and when the damped frequency was calculated, so that came out to be 24 point sorry yes 24.425. The natural frequency was 25.82 and damped frequency is 24.425. And when it was converted into hertz, when it was converted into hertz means divided by 2 pi, so the result that were actually obtained, they were 20. Here you can observe that 24.425 and divided by 2 and divided by pi, this comes out to be 3.887. so the damped frequency that was actually obtained theoretically, that is 3.887 extra. But here, as you have observed, that the damped frequency that the analysis gave, that is 4.6389. so there is you can say appreciable difference, but that is much more closer as compared to the all attempts that I have used. And here you are observing that the modal damping ratio that the ANSYS gave, that is 0.396, but the value of damping factor which I used, that I got, that was 0.323. so there is also a difference of about, you can say, 0.06 units in the modal damping ratio. so you will yourself be trying, and you will be verifying that if there are some discrepancies, or you can further correct it. If you are getting better result, you may let me know. So here in the total deformation, the system will be simulating like this. Actually this analysis was very important. And here another problem which is similar to this, here this problem. so you will be attempting this problem yourself, and I can show you its solution. It is actually in the this was actually figure 2. So that means this is the problem number 2/113, and here you can observe its solution 2.113. and here you can observe that its frequency which has been calculated with 4k by 3, because its equation is like this. And you will be using the same procedure. so important thing is you will be actually, when you will be modeling this system in the slanted position, so you might seek the help for the user defined coordinate system, or you can say some generalized local coordinate system. Means you can insert some coordinate system, and you can define the orientation for these dampers and their coordinates. And remember you will be creating this model at straight 30-degree inclination, not in the horizontal orientation. so you will be solving it and writing its procedure. And if you have any problem, you can discuss it with me. And here is stiffness and damper are parallel, and here another spring is separately attached here. So the equation I have the solution I have shown you. Here you can again observe and this is the equation, and you will be applying this equation, and you can assume the damping factor to be same, for example 0.3 or 0.28 or 0.25 or 0.35, means the value of the damping factor you can assume by between zero point 0.2 at least and zero point 0.4 the maximum, not greater than zero point 0.4 and not below than zero point 0.2. So this is the suitable value. It means you will be assuming the underdamped system, and you will be solving this problem number 2.113. So and again, one important thing is here, that if you want to know, if you have the damped system, and you want to know the natural frequency for this system, so what you can do, that you will be going in the analysis settings, and here simply in the solver control you will be selecting here from the damped no, means if you want the damped solution, then you can select yes from the menu, from this drop down, and if you want undamped, means natural solution, then you will be selecting no from this drop down menu. So if you are again solving it, so you can observe it here. So here you have observed that this is actually the natural frequency in hertz. This is the natural frequency in hertz, which actually theoretically, which I calculated, that came out to be 4.11. 4.11 means 4.11. So here is 1 unit difference. So you will be investigating its issue, and if you have got some better solution, you may let me know. And thank you all. So the contribution for this lab session has been suggested. So if you have any question, you can fairly ask, and please mark your attendance. And thank you all. Assalamu alaikum. God bless you.